Hello everyone, welcome to the second lecture of this course Heat Transfer. Today we will be studying or we will be discussing different numericals based on the concept that we have discussed in the last class. Okay, so in the last class we have studied the different modes of heat transfer and the rate equations. So based on those formulas or the equations of those different rate equations, today we will be discussing different numericals. After that, we will be discussing the one-dimensional heat conduction equation. Okay, so let us start today's class. Now, before discussing the different numericals, first discuss what we have studied in the last class. Okay, we will be discussing those in brief today. So, in the last class, we have discussed the different modes of heat transfer. So, what are the different modes of heat transfer? Actually, there are basic three modes of heat transfer. One is conduction, another convection, and the last one is radiation. Now, what was conduction, if you can remember? So, in case of conduction, it can be defined as the transfer of heat from one part of a substance to another part of the same substance, or from one substance to another in physical contact with it. That means the physical contact is very important, and they are without appreciable displacement of molecules forming the substance. So this was the basic definition of the conduction. Okay, and what we have seen in case of solid, in case of gases, and in case of liquid, how the conduction heat transfer propagates, we have discussed in the last class. Now, in case of this conduction heat transfer, we have studied the rate equation, that is known as the Fourier's law of heat conduction. Okay, so the formula or the mathematical representation of this Fourier's law of heat conduction is given here, which is Q proportional to A multiplied by dt dx. So what is this actually? This Q is the heat flow through a body per unit time. Now, from this mathematical representation, we can say that the heat flow through the body per unit time, it is directly proportional to the area of the section at right angles to the direction of heat flow, and with the change of temperature with respect to the length of the path of the heat flow. Okay, so here dt is the temperature difference of the faces of a homogeneous solid block that we have considered in the diagram. Okay, and dx, it is the thickness of the body in the flow direction. So from this Fourier's law of heat conduction, which we have discussed in the last lecture, so q proportional to a dt dx. So here we have got one constant of proportionality, which is k, that is the thermal conductivity of the body. Now the mathematical representation has been changed as q equals to minus k dt dx. So where from this minus sign we are getting? So there is a physical significance of this minus sign, that is the temperature gradient dt dx, it is always negative along with positive x direction. Okay, and that's why we are putting one minus sign, so that the ultimate final value of the q, that is the heat flow through the body, it becomes positive. So it was the physical significance or the reason behind putting the minus sign in the Fourier's law of heat conduction. Let us discuss in brief the second mode of heat transfer, that is the convection. So in case of convection, the definition is like that: it is the transfer of heat within a fluid by mixing of one portion of the fluid with another. And this convection is possible only in a fluid medium and is directly linked with the transport of the medium itself. So in case of this convection, we have seen that there are two different types of convection. One is free convection or natural convection, and another is the forced convection. Now, like in case of conduction, we have studied the rate equation as Fourier's law of heat conduction. Similarly, in case of convection, the rate equation, it is known as the Newton's law of cooling. So the mathematical representation of this Newton's law of cooling is Q equals to HA into the temperature difference. Now, This Q is the rate of the conductive heat transfer. In this area, it is the area exposed to the heat transfer. And Ts, it is the surface temperature, and Tf, it is the fluid temperature. Now the H in this mathematical representation, it is the coefficient of convective heat transfer. So this Newton's law of cooling, it is applicable for this convection. Next, the last mode of heat transfer, that is the radiation, we have studied. So this radiation, it is actually, it does not require any mode of or any medium in case of the heat transfer, which is required in case of conduction or convection. Now this radiation, it is the transfer of heat through space or matter, and it is thought, or it is anticipated as the electromagnetic waves, or the propagation of the electromagnetic wave, or the quanta. Okay, so radiant energy, it is an electromagnetic radiation, and it requires no medium for propagation, and that's why it may pass through the vacuum. Okay, so in case of this radiation, the formula which is applicable, it is known as the Stefan-Boltzmann law. Now here we can see the mathematical representation of the Stefan-Boltzmann law is given. Capital E, it is the emissive power of the black body. So it is equals to sigma epsilon, then Ts to the power 4. So the statement of the Stefan-Boltzmann law, it is the emissive power of a black body is directly proportional to the fourth power of its absolute temperature. Now this value of the sigma, which is the proportionality constant, the value of the sigma, it is 5.67 multiplied by 10 to the power minus 8. Okay, so this is the Stefan-Boltzmann constant. Now based on these three different rate equations, that is the Fourier's law of heat conduction, then Newton's law of cooling, and Stefan-Boltzmann law, based on these three different equations, today we will be discussing different worked out examples first. Okay, so this is our problem number 1. Let us read the question first. So what it says, a plain wall is 150 millimeter thick and its wall area is 4.5 meter square. If its conductivity is 9.35 watt per meter degree centigrade and surface temperatures are steady at 150 degree centigrade and 45 degree centigrade, then determine number 1, heat flow across the plane wall. So that means heat flow across the plane wall means the capital Q, which we need to find in the first question, and the second one is temperature gradient in the flow direction. So the temperature gradient means dt dx. So from the question, it's after going through the question, we can say that it is a problem of conduction, and we need to use the Fourier's law of heat conduction in this question to determine the required values which is given. Now, what are the things given in here? The thickness of the plane wall, it is given as 150 millimeter. So all the units we need to convert in SI unit here. Okay, so 150 millimeter, it is 0.15 meter. In any of the numerical, in this type of heat transfer, or in any of the subjects of this mechanical engineering, if we take all the units which is given in the question, if we convert those in SI units, then maximum the numerical will be easier to solve. There will be no more confusion in converting what is CGS or FPS or SI, MKS. The confusion should not be there. Okay, so it is better to convert all the units in SI system. Now the area of the wall, it is also given 4.5 meter square. Okay, next the temperature difference, In the question, the surface temperatures are given 150 degrees centigrade and 45 degrees centigrade. So the temperature difference dt, this is T2 minus T1 for the two different surfaces of the plane wall. So the temperature difference equals to minus 105 degrees centigrade. Now the thermal conductivity of the wall material, it is given here 9.35 watt per meter degree centigrade. Okay. Now first we need to find the heat flow across the plane wall. So first we have seen what are the things given. Now what are the things that we need to determine in this question. So we need to apply the Fourier's law of heat conduction here, and we have studied that the Fourier's law, it is Q equals to minus Ka dt dx. So if we apply or use this formula, so here the value of K, that is thermal conductivity of the wall material, it is given here as 9.35 watt per meter degree centigrade. Next, the area of the plane wall, it is also given here, the value is 4.5 meter square. Next, the temperature difference in between the two surfaces of the plane wall, this we have already found out, the temperature difference dt equals to T2 minus T1, it is given here minus 105 degrees centigrade. And the thickness of the plane wall, in the formula it is dx, and here we have considered as capital L, so both are same. So the value for this both, these are same, so it is 0.5 meter, which we have converted from millimeter to meter. So if we put all these values which are given in the question itself, and after calculating using this formula of the Fourier's law of heat conduction, we are getting the value of the heat flow across the plane wall as 29,452.5 watt. Okay, so this is the value of the heat flow across the plane wall. Next, we need to find the temperature gradient in the flow direction. So the temperature gradient is dt dx. Again, we need to apply the Fourier's law. So from the Fourier's law, we can write the value of the dt dx, or the equation equals to minus q by Ka. So the value of this q, that is the heat flow across the plane wall, we have already found out. So we need to only put that value, and the value of the K, that is the thermal conductivity, it was given in the question as 9.35 watt per meter degree centigrade. So we have put this value here. And the area of the plane wall, it was also given in the question. So the value of the area is 4.5 we have entered here, and after calculating all these values in the formula of the Fourier's law, we have got the temperature gradient value as minus 700 degrees centigrade per meter. So in this numerical of this conduction concept, we have applied the Fourier's law of heat conduction, which is Q equals to minus Ka dt dx, and using this Fourier's law, we have found the value of the Q, that is the heat flow across the plane wall. The unit is watt, you need to remember this part, and the temperature gradient, which is dt dx. So these two things we have found by using the Fourier's law of heat conduction. Okay, so let us move to the next numerical. Okay, so in this numerical, let us read the question first. A wire 1.5 millimeter in diameter and 150 millimeter long is submerged in water at atmospheric pressure. An electric current is passed through the wire and is increased until the water boils at 100 degrees centigrade. Under the condition, if convective heat transfer coefficient is 4500 watt per meter square degree centigrade, find how much electric power must be supplied to the wire to maintain the wire surface at 120 degrees centigrade. So from this question itself, we can select or you can understand that it is a problem of the convection heat transfer. And here the rate equation that we have studied is the Newton's law of cooling. So that formula or the equation of the Newton's law of cooling we need to apply here. So in the question, the diameter of the wire, it was given as 1.5 millimeter, which we have written as 0.0015 meter. In the length of the wire, it is also given in the question 150 millimeter, which is 0.15 meter. Now the surface area of the wire, now it is only exposed to the heat transfer. So the side surface area of the wire, the formula for this, it is pi dl. So this type of formula for the cylinder, it is known to us, we are familiar to this. So the formula, it is pi dl. So the value of the d and l, that is the diameter and the length of the wire, it is given in the question. So the area we are getting here is 7.068 multiplied by 10 to the power minus 4 meter square. Now the wire surface temperature, it is given here 120 degrees centigrade, and water temperature, it is given, or water temperature, it is given as 100 degrees centigrade. And the convective heat transfer coefficient, the value of H, it is given 4500 watt per meter square degree centigrade. Now what we need to find here, how much electric power must be supplied to the wire to maintain the wire surface at 120 degrees centigrade. So from the concept itself, we can say that the electric power which must be supplied to the wire to maintain the wire surface temperature, this will be equals to the total convection loss due to the convective heat transfer. Now if it is so, then the Q, that is the total convective heat transfer, its formula is HA into the temperature difference. Now the value of this H, it is given 4500, and the value of the area or the surface area of the wire we have calculated as 7.068 into 10 to the power minus 4, and the two different temperature, that is the wire surface temperature and the water temperature, these two were given in the question. So putting all these values in the Newton's law of cooling, the formula for the Newton's law of cooling, we have calculated the total convection loss or the electric power which need to be supplied to the wire to maintain the wire surface temperature, that will be equals to 63.6 watt. So in this question we have applied the Newton's law of cooling because it is the numerical of the convection heat transfer. Okay, so let us move to the next numerical. So what the question says, air flows over a rectangular plate having dimensions 0.5 by 0.25 meter. So that means the area of that plate we can calculate. The free stream temperature of the air is 300 degrees centigrade. Okay, then at steady state the plate temperature is 40 degrees centigrade. If the convective heat transfer coefficient is 250 watt per meter square Kelvin, determine the heat transfer rate from the air to one side of the plate. Now from this question itself we can say that it is a numerical or from the concept of the convection heat transfer, because the convective heat transfer coefficient and the plate area and the two different plate surface temperatures, these are given, and we need to only determine the total heat transfer rate. So if we can apply the Newton's law of cooling here, we will be able to calculate the total heat transfer rate from the air to one side of the plate. Okay, so here we need to apply the Newton's law of cooling. Now the area for the plate, it is given in the question 0.5 meter by 0.25 meter, and the heat transfer coefficient or the convective heat transfer coefficient, the value is given 250 watt per meter square Kelvin. Okay, so we have got the values of H and A. Now comes the temperature difference. So for these two temperatures, the values are given. One is the free stream temperature, it is given as 300 degrees centigrade, and another is the surface temperature of that plate. So it is given as 40 degrees centigrade. So after putting all these values here in this question or in this formula of the Newton's law of cooling, we have calculated the heat transfer rate from the air to one side of the plate, and the value we have got, it is 8125 watt. So here also we have used the Newton's law of cooling, and using that equation or that formula we have calculated the heat transfer rate from the air to one side of the plate. So this is our number 4 numerical. A surface at 250 degrees centigrade exposed to the surroundings at 110 degrees centigrade convects and radiates heat to the surroundings. So this is a numerical combining the convection and radiation. The convection coefficient and radiation factor are 75 watt per meter square degree centigrade and unity respectively. Okay, so if the heat is conducted to the surface through a solid of conductivity 10 watt per meter degree centigrade, what is the temperature gradient at the surface in the solid? So we need to find the temperature gradient, that is dt dx. We know from the concept of Fourier's law of heat conduction. So that dt dx we need to find here. So let us see what are the things given in the question. So temperature of the surface, it is given. Temperature of the surroundings, it is also given. The convection coefficient, convection heat transfer coefficient, it is given as 5 watt per meter square degree centigrade. The radiation factor, it is given as 1 or unity. The Stephen Boltzmann constant, it is a constant value that we need to remember. It will not be provided in the question. Now this constant value of the Stephen Boltzmann constant sigma, it is 5.67 into 10 to the power minus 8 watt per meter square k to the power 4. This constant value we need to remember to solve these numericals of the radiation. The conductivity of the solid, it is given, the thermal conductivity, it is 10 watt per meter degree centigrade. Now we need to find the temperature gradient, and in the question it is given the heat conducted through the plate, it is equals to the convection heat losses plus the radiation heat losses. So from the first line of the question we have formulated this line. Okay, so the total conductive heat transfer, this is equals to the convective heat transfer plus the heat transfer by radiation. Now in case of the conduction, the Fourier's law of heat conduction, you know, it is equals to minus ka dt dx. This will be equals to the Newton's law of cooling plus the Stephen Boltzmann law. So this is the equation here that we have formulated from the first line of the question. Now in this equation that we have formulated, that is the conductive heat transfer equals to the convective heat transfer plus heat transfer through radiation. In this equation now we have entered all the values which are given in the question. So here you can see that except the value of dt dx that we need to find, that is the temperature gradient. Now except that value, all the other values in this formulated equation is given. So we have entered all the values there, and after putting all the values we have calculated the value of the temperature gradient, and the value of the temperature gradient, it is coming minus 1352.21 degree centigrade per meter. So this is the value of the temperature gradient that we have calculated here. So in this question, all the equations for the three different modes of heat transfer that we have studied earlier will come into play. So the Fourier's law of heat conduction and Newton's law of cooling and the Stephen Boltzmann law. So all these three equations, these are acting here in this single numerical. So if you can remember all these three different equations, we can easily solve this numerical. Okay. So these were the four different numericals that we have discussed till now based on the rate equations of the three different modes of heat transfer. Now let us discuss the one-dimensional heat conduction equation. So there is a diagram given, that is the elemental volume for one-dimensional heat conduction analysis that we have considered. Now if the system is in a steady state, that is if the temperature does not change in time, so this is the concept of the steady state where the temperature, it does not change with time. So if it is means the system is in a steady state, then the problem, it is not very complex and we need to only integrate the Fourier's law of heat conduction. Now if the temperature of the solid is changing with time, solid means the body that we have considered. Now if the temperature of the solid, it is changing with time, that means in case of an unsteady state, if there are heat sources or sinks within the solid, then the situation is complex. So we consider the general case where the temperature may be changing with time and heat sources may be present within the body. So for the element of thickness dx, in the diagram you can see the colored elemental volume. In case of this colored elemental volume, the thickness we have considered of this element as dx. Now to calculate the one-dimensional heat conduction equation, one energy balance is required to be made. So how to formulate or how to make the energy balance here? So to make or to formulate the energy balance in case of this elemental volume for one-dimensional heat conduction analysis, we have considered the energy conducted in the left phase of this elemental volume plus the heat generated within the element. This will be equals to the change in internal energy plus energy conducted out right phase. So from our basic concept of thermodynamics, we have formulated this energy balance equation. That is the energy conducted in the left phase, that is given here as Qx. You can see in the diagram. From the left side, the energy which is conducted in this elemental volume, it is the Qx plus the heat generated within this element. So the heat generated within this element also we have considered. This will be equals to the change in internal energy. So the change in internal energy that will be considered inside this elemental volume plus the energy that will be conducted out from the right phase of this elemental volume, which is Qx plus dx. Now if this is our energy balance equation, we need to find the equation for these four different things. So how to formulate or how to write the equations for this energy balance? So the energy in the left phase, which is Qx, this formula we can write from the Fourier's law of heat conduction. So Qx equals to minus Ka del T del x. So we know this formula. Now the energy generated within the element. So if the area is considered as capital A, then the energy generated within the element, it is equals to the Q dot multiplied by the area and the thickness of the elemental volume. So this is the energy generated within the element. Now what is the right hand side of the energy balance equation? It is the change in internal energy and the energy conducted out in the right phase. So what will be the change in internal energy? So the change in internal energy, this is equals to, from we can say it is the mass multiplied by the specific heat and the temperature difference. So we have seen this concept in our thermodynamics. So we can write the equation for this change in internal energy as mass multiplied by the specific heat, and it is also multiplied by the temperature difference. So the mass equals to rho a v, that formula we know, and the specific heat, it is C, and the temperature difference. So the multiplication of these three different terms is giving us the change in internal energy. Next, the energy out in the right phase. So what is the energy out in the right phase? It is equals to Qx plus dx. So dx is actually the thickness of the elemental volume that we have considered. So Qx plus dx, that means the equation of the Q, it is minus Ka dt dx, which we know from the Fourier's law of heat conduction. Now, how to write the expansion of this equation? So from our concept of Taylor series, we have written this expansion of this equation. So from the Taylor series, we know fx plus h equals to fx plus f dash x into h up to two terms. So using that concept of the Taylor series expansion, we have written the expansion of this qx plus dx, which is the energy out in the right phase of this elemental volume. Now here the q dot, it is the energy generated per unit volume, and the unit of this q dot, it is W per meter cube. C is the specific heat of the material, and rho is the density, the unit is kg per meter cube. So from the energy balance equation, if we put all those equation in our energy balance equation, then after two or three different steps, we will get the final equation like this: del del x of k dt dx plus q dot, which is the energy generated per unit volume, equals to rho c into del t del x. So this is the final version of the one-dimensional heat conduction equation. Okay, so here what we have done, we have taken one elemental volume, and for that elemental volume we have formulated one energy balance equation, and for that energy balance equation we have determined the one-dimensional heat conduction equation. Now, using this concept of this method of the one-dimensional heat conduction equation, we will formulate the heat conduction equation for a three-dimensional body. Okay, so the 3D heat conduction equation will be discussed in our next lecture. Okay, there we will study this three-dimensional heat conduction equation in Cartesian coordinate, in spherical coordinate, all these things. After that, what is thermal diffusivity, the definition, the concept, and the physical significance of this thermal diffusivity, we will study in our next lecture. Okay, and based on different formula, we will try to discuss different numericals in our next lecture. Okay, so this is the end for this lecture 2. We will discuss the next topics in our lecture 3. Okay, so thank you very much.